Good morning. Welcome to the 43rd lecture on economics, management and entrepreneurship. In our last lecture, we were discussing inventory management. Today, we shall continue to discuss the same topic. First, let us recall that towards the end of the lecture, we were discussing about how to control inventory in the simplest of the situation, where we assume demand to be continuous, constant and known, and lead time, supply lead time is equal to 0. We can show this in the form of a diagram such as this. In this diagram, the x axis is time and the y axis is the on hand inventory. If we have a maximum amount of inventory held as Q and lambda is the demand rate and T is the cycle length, then after T time this Q will be depleted to 0, inventory will be depleted to 0, and then we place an order for Q items, and since the supply lead time is equal to 0, it is immediately obtained in the stock, and then because of the continuous demand it continuously falls, and this continues in a cyclical manner. This looks like sawtooth, and therefore, this diagram is known as a sawtooth diagram. The costs associated with such an inventory replenishment policy are two. One is the procurement cost K plus C Q, and then the inventory holding cost. The average inventory held is Q by 2 and multiplied by T is the inventory held in the T cycle time, and I C is the inventory holding cost I C per unit multiplied by this. So, this is rupees per unit per year, and this comes to K plus C Q plus I C Q by 2 into T per cycle. Now, per year it will be 1 divided by T, that makes it K by T plus C lambda plus half H lambda T. And once we have such an expression containing T, we differentiate this with respect to T, we get the optimal value of T star that minimizes the value of total cost, and then since we know that Q star is nothing but lambda T star, we can get this expression which is root over 2 lambda K divided by H. In the numerator, we have the demand rate lambda. If demand is more, then Q has to be more, but if the fixed procurement cost or ordering cost is high, then Q star should also be high, but if the inventory holding cost is more, inventory should be, the amount ordered should be less. This looks like this contains a square root, therefore, this formula is called a square root formula. It is also called Wilson's lot size formula. So, from here we answer two questions. When to order? We order when the on hand inventory is 0, and how much to order? We order Q star, which is equal to 2 lambda K divided by H. Now, here we are showing how the costs vary with the amount of Q. As Q increases, the inventory holding cost increases, and but the procurement cost reduces. The total cost takes a minimum at the value Q star. Now, all this we had discussed in our last class. We would like to take up more realistic cases of lead time not constant to start with, and then we shall relax many of our assumptions. We shall take up cases when demand is not known, is not constant, but is probabilistic. We shall also consider the case of lead time being probabilistic. To start with, we shall consider the case of deterministic demand, but the lead time is not 0, but less than T, the cycle time. So, it is very simple. how much to order remains the same, q star 2 lambda k root over 2 lambda k by h, but when to order is lambda or delta time before the inventory comes to 0. That means, when the inventory position is delta multiplied by lambda, that is the time, that is the reorder level. We call it the reorder level. At this point, when the inventory comes down to the level of lambda into delta into lambda, this amount, place an order, and after delta time, which is called the lead time, the amount is obtained in the stores. Continue to do this, when once again it falls to the level delta into lambda, place an order for q, and the amount will come at this point. So, this is the case, but sometimes the lead time can be greater than t. Say for example, here we are considering lead time as big as this. So, we still order. So, what we do? We consider lambda delta minus m t, where m is the largest integer less than or equal to lambda by t. So, in this case delta by t is 1 point something. So, take m as 1. So, consider this, that means, you order still at the reorder level is still delta into lambda, but the quantity arrives only after delta time, it arrives here. So, when this has arrived because of a demand or replenishment order that was placed sometime at this point, and when it comes down to the level of delta into lambda, place an order for q, and that will come after delta time again. That means, this is due to a demand or due to a replenishment order that was placed at this point of time, and similarly it continues. So, this is the case when delta is greater than the cycle or the cycle time t, capital T. We take an example to illustrate this case. Let us say that the annual demand is 1000 units per year. The order cost is rupees 10 per order. So, this is k is 10 rupees per order, lambda is 1000 units per year, holding charge which is I into C h is 20% per year. So, we take 0.2 per year. The unit cost of the item is rupees 10 per unit, 10 rupees per unit, and the supply lead time is 50 days, Now, here we straight away use our how much to order is q star, which is given by root over 2 lambda k by h. We put the values, we get this as 100 units. Now, when to order will be determined by first of all knowing the cycle length. We know the supply lead time is 50. The cycle length is nothing but q star divided by lambda, that comes to 0.10 year, which is something like 36.5 days, but the supply lead time is 50 days. So, delta divided by cycle time is 1.37, that is 50 divided by 36.5, and the largest integer less than or equal to this value is 1. Therefore, reorder point ROP is lambda times delta into MT, which is equal to 1000 multiplied by 1000 multiplied by this quantity, which comes to 37 units. Now, because this is 37 units, when the inventory level comes down to 37 units, we place an order for 100 units. So, we thus know when to order when the inventory position comes down to 37 units, and how much to order is 100 units. This is the economic lot size. Now, we take up another case. We say that the order is replenished by the factory itself by producing the amount that is ordered. So, this is a question of, this is a case of finished product inventory. So, in the finished product inventory case, we still assume that the demand from the customer is constant and is known, whereas the supply is not instantaneous. It does not take place in one lot, but it is continuously produced and is available at the stores, because it is produced at the factory. We are plotting that case here. We are plotting on hand inventory against time. We are saying that the production facility is used for different types of purposes. For this particular product, whenever there is an order, it produces for some time, we are calling it TP, the production period. So, it is producing certain amount for this product, and then the facility is used for some other product. Because we are considering only this particular product, we are assuming that TP is the production time, and suppose that psi is the production rate. During this period also the demand of lambda is taking place. Therefore, the rate at which the inventory rises is the production rate minus the demand rate, and at this point the quantity, total quantity demanded for production for replenishment is available, and therefore, no more production takes place for this particular item. From this time onwards, the on hand inventory reduces as per the demand rate lambda. So, the slope is minus lambda here, and then it comes to 0. At this point, once again the order is placed for production, and once again the inventory rises and it falls. Therefore, it still in this case also we can see cycle, but it is not a sawtooth type of a curve. It has a rising straight line here, first phase for TP time, and for TD time. TD time is the time to deplete the maximum on hand inventory to 0. So, we see that psi minus lambda multiplied by TP is equal to TD multiplied by lambda. So, if Q is the amount that was ordered, then the maximum inventory that we shall hold is Q multiplied by 1 minus lambda divided by psi. So, this is the maximum amount of inventory. Once again, the total cost per cycle is the order cost, fixed order cost, and that is for us the setup cost. For every product, for every order that is received for a different product, the machine has to be set up. So, that there is a setup cost involved. So, for this particular case where production is involved, we call it the setup cost. K plus CQ plus same thing IC multiplied with the average inventory held. The average inventory is the maximum inventory divided by 2. Maximum inventory is this Q into 1 minus lambda by psi multiplied by T. And proceeding as we had done earlier, we can find that Q star, the optimal value of Q that minimizes this total cost per year, is 2 lambda k by ith root over multiplied by another factor. And this 2 lambda k divided by ith root over is nothing but the Wilson's lot size. We are writing W here to indicate that this is Wilson's lot size. So, Q W which is root over 2 lambda k by h multiplied by this factor 1 divided by 1 minus lambda by psi. That is the amount to be ordered. So, when to order is when on hand inventory comes to 0, and how much to order is Q star is equal to Wilson's lot size formula into 1 divided by 1 minus lambda by psi root over. We take an example, similar example as before. The annual demand is 1000 units. The setup cost is 10 rupees per year, holding charge is 20% per year, the unit cost is rupees 10. Now, we have added the production rate as 1500 units per year. So, we have already found this is the same case as before, excepting that the production rate is 1500 units per year. So, Wilson's lot size is nothing but 100 and Q star is nothing but Q W into this, that is 100 divided by this, that comes to 176 units. That means, we should order for 1076 units, and from there we can determine the cycle time, which is the total quantity consumed in that time, cycle time. Therefore, this divided by the demand rate, that comes to 64.24 days, and production run time we can find that as 42.80 days. The remaining time where there is no production and the demand is existing, and therefore, the inventory level comes from the maximum value to 0 level is 21.44 days. So, we have considered two cases. The simplest case of demand is constant and the instantaneous supply of order, and the second case we have taken when the supply is not instantaneous, but is continuous because it is produced in house. Now, there are many such variations of this economic order quantity formula, but we will not consider all those cases. In any standard textbook you can get them. We are now considering the case when there is a variability in the demand and when the lead time is also variable. Now, when there is a variability in demand, naturally you will have to keep little more stock, because there is much greater variation in the demand. That means, around the mean value of the demand there is a variation. Therefore, whereas earlier you could predict, because demand was constant, lead time was constant. Therefore, you could know that during the lead time, if lambda is constant and the lead time delta is constant, then delta into lambda is the stock that you should have. But now that you know that there is a variation in the demand, you must keep more than this amount. This amount that you should keep to account for the maximum demand that can occur during the lead time beyond the expected demand during the lead time is called the buffer stock or the safety stock. So, in dealing with the variability in demand, we create buffer stock, and how much buffer stock or safety stock we should keep is basically a policy of the management. Management specifies a service level. A service level basically says that this is the probability that the demand during lead time will not exceed the stock level so much percentage of the time. So, if it says that it does not expect 5% of the time during a particular cycle, then it means that the management policy is that the service level is 95%. If instead the management policy is that at any time the safety, the maximum demand during the lead time should not exceed the inventory by more than 1%, it means that its service level is 99%. So, this is how the service level is defined, and the reorder level then is, first of all, this is the expected demand during the lead time, assuming lead time is constant, and even though demand is varying, we take the average value. Average demand of the lead time is the expected demand during the lead time. Remember that we are assuming lead time to be constant, but demand variable. On top of this, in addition to this, we have to store buffer stock, and the amount of buffer stock is a function of the service level that the management decides. It is like this, that you see, this is the time when we are placing an order for replenishment. On hand inventory is falling, and when it reaches a reorder level, we place an order for an amount q, and it arrives after a constant time. Now, you see that this the way it is reducing is not a straight line, meaning that the demand rate is not constant, it is varying, and it is expected that one would like that the inventory should not come to 0 during this lead time. Now, here is the situation that it is not 0, but in the second cycle you will see that when we get the replenishment and then once again it falls, it is possible that it before the next replenishment takes place, which occurs after this lead time, the same lead time, the inventory has come down to 0, and this small time length is the period for which we have an stock out condition. So, what is normally done is that the reorder level is just not the expected demand. Expected demand is basically the average demand into the lead time, probably only this much is the expected demand, but on top of this we in fact should think of a maximum demand that can occur during this time, and we should create a little more stock, and that is called the planned safety stock. That depends, what I said, on the service level. So, this is a case of variable demand, as you can see, variable demand and constant lead time. Now, how we handle? We handle using probability theory. If lambda is the daily demand rate, which is considered a random variable and follows a normal distribution with mean mu and variance sigma square. So, we have to use probability theory concepts. So, if you do not have a good background in probability theory, then it will be difficult for you to understand this, and we are not discussing the concepts of probability theory. I request you to go through any book on probability theory, and this is very simple introductory material in any book on probability and statistics. Here we are assuming that the lambda is a random variable that follows normal distribution with mean mu of demand d and a variance sigma square. Then the total demand during the lead time lambda L is a sum of L random variables, because it is let us say the daily demand rate. So, every day lambda is varying. So, if L consists of so many days, so it is a sum of L number of random variables, and the variance, the mean of such a random variable lambda L, which is the sum of L random variables, is L times mu d. The mean mu d plus mu d plus mu d plus mu d L times, and variances are also added, sigma square plus sigma square plus sigma square L times, because there are L number of such random variables that are added. We are trying to define the sum of L number of random variables lambda I. So, means are added and variances are also added. Therefore, lambda L follows normal distribution with mean mu d into L and variance L into lambda square, where lambda I is the demand on the ith day. So, basically we are saying that this is the normal distribution whose mean is mu d into L, and we are plotting lambda L the sum of, that means the total demand during the lead period, lead time, and if the service level is 95%, that means we are interested to keep a service level here such that the maximum demand will exceed this value only 5% of the time. So, the area under the normal distribution is 0.05. If the area under the normal distribution is 0.05, then by how much, if the mean is mu d into L and if the variance is root over L, this is the standard deviation, root over L into sigma into Z, the standard normal random variable. From the normal distribution table, we can find the value of Z as 1.645. So, normally normal distribution tables are available in the appendix of any book on probability theory, and one can find out corresponding to 0.05 what is the value of Z, and the value of Z is 1.645, and such a distribution whose mean is this and the variance is lambda L can be standardized by a standard normal random variable, which is lambda L minus the mean divided by the standard deviation, which is root over L sigma. Such a standard normal random variable has a mean 0 and a variance 1. So, this value of lambda L is equal to mu d L plus Z into this, or for this the value is Z is equal to 1.645 for 0.05. Now, this requires a little bit of knowledge of, as I said, probability theory, which is quite simple. Now, how do we then calculate the buffer stock? Buffer stock then is equal to the maximum demand during the lead time that can be made by the buffer stock at the specified service level minus the expected demand during the lead time. So, for us this is the maximum demand at the service level, specified service level, that corresponds to the value of Z, minus the expected demand during the lead time is mu d into L. So, this quantity Z into root over L into sigma is called the buffer stock. If 95% is the service level, buffer stock is equal to 1.645 multiplied by the standard deviation, which is the root over of the variance. Normally, Z is called the safety factor. We take an example to illustrate this case. The average usage rate of an item is 100 units per day. The standard deviation of the daily demand is 5 units per day. The lead time is 9 days. The firm desires a service level of 95%. Find the buffer stock and the reorder level. So, what are given are the mean value of the demand, which is 100 units per day, variance is given as 5 units per day, lead time is given as 9 days, service level is given as 95%. Buffer stock is then corresponding to 5%, which is 1 minus service level from the normal distribution table. Z is 1.645. I am sorry, this is not correct. This is 1.645. So, this calculation may be wrong, but you make the calculations. So, buffer stock is equal to 29.4 units. It means that by keeping a buffer stock of 29.4 units, there will be one stock out in 20 replenishment cycles, because 5% is the stock out in one replenishment cycle. Therefore, in 20 replenishment cycles there will be one stock out. This is the meaning of the service level. The reorder level is the expected value of the demand during lead time plus the buffer stock. The expected demand during the lead time is given by the average usage rate 100 multiplied by the lead time 9 plus the buffer stock, which is 29.4. Therefore, the value of the reorder level is 929.4. It means when the inventory position comes down to 929.4 units, you place an order for Q and you are then taking, or you will then ensure a service level of 95%, meaning that there will be a 5% chance of a stock out, meaning that there will be one stock out in 20 such replenishment cycles. Now, we consider the case when the lead time is variable, but the demand is constant. So, here demand is constant at mu d, but the lead time L follows normal distribution with mean mu L and variance sigma square L. Here the reorder level is as before, the average value, expected value of the demand during the lead time, which is mu d into mu L plus a buffer stock created, because the lead time itself is changing, and that is Z into sigma L into mu d. Mu d is the mean value of the demand, constant value of course, mu d into Z sigma L. We take an example. Suppose the demand is 25 units per day and L has a mean value of 9 days, but it has a standard deviation of 2 days, then the lead time is normally distributed, and suppose that the service level is 95%, then the buffer stock is, just apply this one, mu d Z sigma L, Z is 1.645 from normal distribution table, sigma L is 2 days and mu d is 25 units, that comes to 82.25 units. The reorder level is the expected demand, that is 25 into 9, which is 225 plus 82.75, that makes it 307.25 units. So, this is the case of constant demand and variable lead time. Now, we can consider the more general case of variable demand and variable lead time. Now, this is more difficult, and one can of course go for analytical solution. However, one can also go for simulation, because it is a little more complex case. That is what we are writing here. The demand follows normal distribution with mean mu d and variance sigma square, and the lead time L also follows a normal distribution with mean mu L and variance sigma square L. One can go for analytical solution, but one can also go for simulation. Now, although we have assumed that the demand and the lead time vary according to normal distribution, they may not actually follow normal distribution, they may follow any other distribution. Then the cases are even more difficult to handle. The natural solution for such cases is by resorting to simulation. Now, in these cases we have considered the independent demand case. Before we go for the dependent demand case, we will give some more insights into the service level. As already I have told, the chance of stock out service level 100 into 1 minus service level is the probability that the lead time demand is greater than buffer stock. Thus, 95% service level means lead time demand exceed buffer stock 5% of the time. Thus, the chance is 5% stock out in one cycle. If the order quantity is Q and is given 20 times a year, then the expected number of shortages is 0.05 into 20, which is 1 per cycle. If the order quantity is TQ and is given 10 times a year, then the expected number of shortages is 0.05 into 10, which is 0.5 per year or 1 in 2 years. Now, Sometimes we are also interested in finding out the number shortage, not times the inventory is out of stock, but the number of units which are short. This is the expected shortage. Now, without deriving the formula, we are showing results that have been arrived at by various researchers. They have shown that the ratio of expected quantity short, number of items short, to the standard deviation of the lead time demand is a function of the safety factor Z, and they have given tables such as this under the assumptions of normal distribution of the lead time. So, Z is the safety factor, the ratio expected number of units short by the standard deviation of the demand is given by this for different service levels. Thus, if the service level is 95% that the management has set, and if sigma d, the demand standard deviation, is 9, then the expected shortage for 95% is 0.02089 multiplied by sigma d, which is 9, is the expected shortage per order, that comes to 0.189 unit per cycle. So, expected shortage per year is 0.189 into number of orders per year. So, one can thus find out the actual number of units short in a year, the expected number of units short per year. So, if the number of orders per unit per year is 10, then 0.189 into 10 is 1.89, those many units are short. So, one can thus find out the shortest cost, which is the expected shortage per year multiplies by the unit shortage cost. So, in addition to our two costs that we have considered for finding out the economic order quantity, namely the ordering cost and inventory holding cost, we can also consider the shortage cost. To find out the shortage cost, we have to find out first the number of units short, and then we must have an estimate of the cost of shortage of one unit, and that depends on two conditions: whether it is a case of back order. If certain unit is short, then there is a possibility that the demand that is coming is held back as order backlog. That means, the order is received and is not cancelled. It is held because the customer can wait for some time, and he will fulfill the order at a later point of time. This is a case of order backlog or back order case, and the other case is the lost sales case, in which the order is received, but because you do not have enough inventory, you cannot fulfill the order, and therefore, it is lost. The customer does not wait. In any case, for both the situations, there are costs involved. The back order cost in the first example or the first case, and the lost sales cost. And the back order cost is that there is a cost of disruption. You have to specially handle this request or this back order and go for expediting it. There is a loss of customer goodwill, and then in the lost sales case, there is a total loss because of the contribution or the revenue is completely lost. So, one has to estimate the unit shortage cost, multiply that with the expected number of units short to find out the shortage cost per year, and following the other two, one has to also estimate the ordering cost and the inventory holding cost, add to that the expected shortage cost, and then follow the same procedure to find out the economic order quantity. So, friends, we have considered till now the case of independent demand. Now, we shall consider, even before that, let me introduce we can find out Q, but how to actually operate the inventory, there are different models for that. The first model is called the transaction reporting system or the fixed order system, also known as QR model. Q is the fixed amount of order or the lot size, reorder point, lot size Q. Whenever items are taken off, the inventory records are updated immediately. That is why it is called transaction reporting system. Order Q amount, the fixed order or the lot size order, when the stock level falls to X, X less than R. That means, when the inventory position falls to less than R, place an order for Q. And a variation of this model is the RR model, where whenever the inventory level falls to X, X less than R, order up to level R, not an exact quantity Q, but up to level R. So, these are the two variations. So, this we are plotting here. This is the inventory and this is the time axis. This is the reorder level calculated the way we have already decided R, and this is a QR model. So, inventory is falling, this is farm line is the inventory line. As the inventory is falling, somewhere here it reaches the reorder level, place an order Q and the lead time is this. This is the lead time. After that it comes. The replenishment arrives after the lead time. By that time the inventory is depleting. So, when the inventory comes, it is here. Once again the inventory starts falling, at some time the inventory falls to R or less than R, we place an order for Q. So, this dotted line says the inventory position, which is the on hand inventory plus the on order inventory minus the back order. So, there is no back order here. So, it is 0, on hand inventory plus the on order inventory. So, this arrival occurs because of a prior order that was placed some time back. So, the inventory position here, the total inventory position on hand plus on order, and there was assuming no back order. So, it was falling like this. Now, at this point the order arrives, again it falls, again here we have placed an order, therefore, the on hand plus on order becomes this. By that time the actual on hand inventory position reduces, therefore, the inventory position also reduces, and after lead time, which is not fixed. So, orders are placed here and stocks are received against the order here and here. So, these are the lead times, this and this. This is the QR model. Compare that to another type of a model which is called periodic review model. Here we place order after every review period capital T, and there are quite a large number of variations. RT model, that is order up to R, RRT model, if inventory is less than or equal to R, then order up to R, or NQRT model, order a constant times Q, n can be 1 or 2, such that inventory is less than or equal to R. So, there are many variations, we show them in this curve, in this graph. This is the on hand inventory, this is the RT model, and this is the T. At every T we place an order. So, at this point we place an order for Q item. Actually, we should have drawn a line like this, a dotted line like that, because then it would have shown the inventory position. Okay. Now, at this point we place an order up to R, and then it comes at after L1 period, and then at this point we once again place an order. You can see that the order quantity is different. Here the order quantity is Q1, that comes here. Here the order quantity is Q2, because we are all the time placing an order up to R. So, here it is different. So, what is constant here is the T, the period, length of the period, that is constant, but amount is order is placed is different. So, this is another way of also operating the inventory, and it has been seen that the average inventory held in a QR model is more than that in the periodic review model, because in the QR model we have to keep a buffer stock, and that makes the value of the average inventory held more than the amount that is held in a periodic review model here. So, we have considered the inventory situation in great detail so far, but all those cases we have considered are for independent demand case. We shall end our lecture by discussing on the dependent demand case. And the best way to consider a dependent demand case is by considering MRP, the materials requirement planning. Now, first of all, what is this case of dependent demand? It is ideal for companies assembling end items from components in batch manufacturing processes. That means, if you have to assemble certain units or certain components, and if the number of assemblies is to be produced is known, then the number of components is automatically known. So, one has to therefore have three things: master production schedule, bill of material, and inventory file. We give an example to illustrate what we are saying. A unit of product A is made up of 2 units of subassembly B and 2 units of subassembly C. In turn, 1 unit of B is made up of 2 units of component D and 1 unit of component E, whereas 1 unit of C is made up of 1 unit of component D and 2 units of component F. Now, it is basically they are saying, it is saying that the final assembly is made up of 2 subassemblies. Each subassembly is in turn made up of 2 components each, and the lead time to manufacture or buy the parts are this: 1000 units of A, the final assembly, are required. Find the order quantity and the date of order for each subassembly and component if the final assembly A is to be delivered on 7th of August. You can see that the demand for various items B, C, D, E, F are all defined once the demand for A is known, and the demand for A is known 1000 units. Therefore, the demand for B, C, D, E, F are known. This is the case of dependent demand. Now, this relationship that A is made up of 2 subassemblies, each subassembly is made up of 2 components, can be shown in the form of a product structure diagram. A tree structure: A consists of B and C, B consists of D and E, and C consists of D and A, F. This within parenthesis says that 1 unit of A requires 2 units of B and 2 units of C. 1 unit of B requires 2 units of D and 3 units of E. 1 unit of C requires 1 unit of D and 2 units of F. Also written here is some numbers 1, 2, 2, 1, 2, 3 and 2. They are all lead times. Once the work starts, it will take 1 day or 1 week, in our case 1 day. Once we place an order for B, it will be available after 2 days, etc. Now, we show this in this form. A, B, C, D, E, F are the parts, final assembly, 2 sub assemblies and different parts. We need to have A 1000 units and it has a lead time of 1 week. Therefore, order for item A must be placed 1 day before, that is on 6th of August. Now, to make 1000 units of A, we need 2000 units of B and 2000 units of C, 2 items of B and 2 items of C for every unit of A. And B's lead time is 2 weeks, C's lead time is 3 weeks, and therefore, there is a lead time offset. Order must be placed for B 2 days in advance and 3 days in advance for C. So, for C again the required date for D and E are mentioned, and like this one proceeds backward. So, one has to proceed this way and proceed that way. So, we finally get to know that on the day 1 order must be placed for F and for D, these many items. On day 2 order should be placed for D. On day 3 order should be placed for E 6000 items and for C 2000 items. Day 4 order should be placed for 2000 items for B. On day 6 order should be placed for A 1000 items. This is a very simple example of materials requirement planning. So, what we have done so far is that we have exploded our gross requirements and to net requirements, offset the order for these requirements considering their lead times, which is also known as back scheduling, and we have ordered for lot. You see, the lot size is not constant. What can be done is lot sizing to reduce setup cost. One can also have a safety stock to take care of uncertainty in demand during lead time, and one can also give a little more lead time as a safety, just 1 or 2 days more. So, friends, inventory control is quite extensive. There are large number of topics. We have covered some topics, particularly the deterministic demand and lead time cases. Today, we considered the probabilistic lead time and probabilistic demand cases. We introduced the concept of buffer stock. We also said that in practice, either fixed order system is followed or fixed period system is followed. Towards the end of the lecture, we introduced the dependent demand case, and we will take up one more topic on inventory management in our next class before going to a new topic, and that topic will be supply chain management. Thank you very much.